This FRQ says the height of a tree at time t is given by a twice differentiable function h, where h of t is measured in meters and t is measured in years. Selected values of h of t are given in the table above. Part A. Use the data in the table to estimate h prime of 6. Using correct units, interpret the meaning of h prime of 6 in the context of the problem. To find h prime of 6, we're going to use these data values because 6 will fall exactly in between 5 and 7. For h prime of 6, you end up getting 5 halves. In context to the problem, h prime of 6 is the rate at which the height of the tree is changing and then units are meters per year, specifically at the time when t is equal to 6 years. Part B says explain why there must be at least one time t between 2 and 10 such that h prime of t is equal to 2. It's important to notice that even though it doesn't specifically say to use the mean value theorem, that because of the wording, that's what we're actually supposed to use. And so this would be the f prime of c part. They're already giving us that it's equal to 2. So we want to find two data values in between 2 and 10 that when we take the average rate of change, we'll get the same value too. So you want to look through the table. So I want to look right here with these data values. Our change in y is 4 and our change in x is 2. So 4 over 2 would make 2. Okay, so h of 5 minus h of 3 all over 5 minus 3 ends up equaling 2, which is the same as h prime of t equaling 2. So then we write, because h is differentiable on the interval from 3 to 5, h is therefore continuous on the interval from 3 to 5. By the mean value theorem, there exists a value c in between 3 and 5, such that h prime of c is equal to 2. Part C says use a trapezoidal sum with the 4 sub-intervals indicated by the data in the table to approximate the average height of the tree over the time interval from 2 to 10. To find the average height of a tree over a closed interval from 2 to 10, you're going to use the average value formula. One over 10 minus 2, the integral from 2 to 10, h of t dt. So you get 1/8, the integral from 2 to 10, h of t dt, and then we want to use the trapezoidal sum with 4 sub-intervals to find the integral from 2 to 10, h of t dt. Remember, your formula for trapezoid is 1/2 the height times the quantity base 1 plus base 2. So here you have a height of 1 times base 1 plus base 2. And then you have the height of 2 times the quantity base 1 plus this base 2. And so on. This height is 2 and this height is 3. So to set this up, I dropped the 1/8 down. Since every trapezoid has a 1/2 in it, I pulled the 1/2 to the front. This is the height of 1, and then you have base 1 plus base 2. And the next trapezoid, a height of 2, base 1 plus base 2. Height of 2, base 1 plus base 2. And then you have a height of 3, and then here's base 1 plus base 2. Okay, so you end up getting 263 over 32. Part D says the height of the tree in meters can also be modeled by the function g, where g is equal to 100x over 1 plus x. X is the diameter of the base of the tree in meters. When the tree is 50 meters tall, the diameter of the base of the tree is increasing at a rate of 0.03 meter per year. According to this model, what is the rate of change of the height of the tree with respect to time in meters per year at the time when the tree is 50 meters tall? So first it says when the tree is 50 meters tall, so we can take 50 and we can set that equal to 100x over 1 plus x to solve for x. So 50 equals 100x over 1 plus x. When you cross multiply, you distribute the 50 to the 1 plus x, and you get 50 plus 50x equals 100x. Subtract this 50 over, so you get 50 equals 50x, therefore x is equal to 1. Next, it's asking for the rate of change of the height of the tree with respect to time. So we're going to take g, and we're going to take the derivative with respect to time. G has x's on top and bottom. We're going to do the quotient rule. So the derivative of g with respect to time, I started with low, 1 plus x, and then d high, so the derivative of the top is just 100, but because the top had 100x, and x is not t, we're going to times by dx dt, minus, and this is high, and then d low, the derivative of 1 plus x is just 1, and again, because x is not t, we're going to times by dx dt, all over the low squared. And we're going to evaluate this derivative when x equals 1. It also specifies that the diameter of the base of the tree is increasing at a rate of 0.03 meter per year. And so 0.03 is going to be our dx dt, because it says x is the diameter of the base of the tree in meters. Okay, so we're plugging in 1 for x, and we're plugging in 0.03 for dx dt, we get 3/4. Okay, so the rate of change of the height of the tree with respect to time is 3/4 meter per year when the tree is 50 meters tall.